We are going to be solving UTME questions on gravitational field. Now the first question. The force with which an object is attracted to the earth is called its dash. Is that force called its acceleration, its mass, its gravity, its impulse, or its weight? Obviously the answer is its weight. Force can never be what? Mass or acceleration. So we have what called gravitational force, but the force, that which that object is self-experienced is called its weight. And I think we did, I explained that during last lecture. Next, the force experienced by an object of mass 60 kilograms in the moon's gravitational field is, what's the force? 1.002 times 10 to the power 2 Newton. What is the intensity of the field? What is the electric intensity? Force per unit mass. As simple as that. So we just divide straight. So the force is 1.002 times 10 to the power 2, and the mass is 60 kilograms. This becomes 100.2 over 60. I believe you can finish yourself. The unit is what? Newton per kilogram. In short, they are asking for the acceleration due to gravity. So let's for example, what if you are told that what is the acceleration due to gravity in that field? So once you get the value of E and G, they are equivalent. On Earth, 10 kilogram, so 10 Newton per kilogram equals to 10 meter per second squared, approximately. I explained that in the lecture. So any value you get, just change it to meter per second squared. That is also acceleration due to gravity. Next, a body is projected from the Earth's surface with the intention of letting it to escape from the Earth's gravitational field. What is the minimum escape velocity of the body? Ordinarily, with this question you ought to solve, but if you listen to the lecture, you don't need to solve. The answer is this straight. And what's the formula? V equals to square root of 2gr, where r, is the radius of Earth. In this case, you're not even given the radius, so it is expected that you should know the value itself. Circular orbit, 8 km per second. Elliptical orbit between 8 and 11. Greater than 8, less than 11. Next, a planet has a mass m1, and it is at a distance r1 from the sun. A second planet has a mass m2, and that m2 equals to 10 m1, meaning the mass is 10 times bigger, and is at a distance of r2, and that r2 equals to 2r1 from the sun. Determine the ratio of the gravitational force. You are looking for F1 to, let's say, F2. So what is F1? F is Gm m1 over what? r1 divided by Gm m2 over r2, because F is Gm over r. So from here, what happens? We can write this as F1 over F2 equals to, let's just take the division to multiplication. So from here, F1 over F2 equals to Gm m1 over r1 times, when we change division to multiplication, this goes up, r2 over Gm m2. What happens here? Gm cancels Gm, so from here it means F1 over F2 equals to m1 over r1, m1 over r1 times r2 over m2. But what is r2? r2 is 2r1, 2r1 over, what is m2? m2 is 10m1, 10m1. What happens here? m1 here 1, m1 here cancel, r here 1, r here cancel. So the answer is 2 over 10, which is what? 1 over 5. So the ratio of F1 to F2 equals to 1 ratio 5. As simple as that. Now consider this question. If the distance between two suspended masses, 10 kg each, is tripled. So let's suppose the initial distance is r. The initial distance r2 is what? Tripled, 3r. Then ask, the gravitational force of attraction between them is reduced by what? Recall I gave you the formula. F2 equals to F1 R1 over R2 all squared. So directly let's apply this. So F2, the new force, equals to F1 into what is R1? What is R2? 3R all squared. So it means F2 equals to F1 into 3R1, that's 1 over 3 all squared. Then F2 equals to F1 times 1 over 9. So the new force is what? 1/9 of the initial force F1. So what's the answer? The answer is option B, 1/9. Secondly, a satellite is said to be in a parking orbit if its period is dash. With Earth, for example, I said in the lecture, for a body to be in a parking orbit or for a satellite to be in a parking orbit with Earth, it must have the same period of revolution with Earth. In the options we have less, greater, square, and the likes. The answer is its period is equal to that of what? Earth. Then lastly, the Earth is 4 times the size of the Moon. So size, we're talking about radius. So you can say the radius of Earth, let's call it RF, is what? 4 times R Moon. Let's suppose this Earth and this Moon. So we can use their radius to represent their size. And the acceleration due to gravity on Earth, that's G on Earth, is 80 times that of the Moon, 80 G Moon. Question is, the ratio of the mass of the Moon to that of Earth is, you are looking for M Moon over M Earth and the Moon. To solve this, let's start with this. What is the formula to calculate acceleration to gravity? If you recall the formula, G itself equals to Gm over R squared. So for Earth, this will be GE-MERE. For Moon, it will be MM over RM all squared. But if you notice something is not changing, what is not changing? This G is a constant. Or let's just make M the subject here. From here, if you make the mass of Moon the subject, the mass of Moon equals to G Rm squared over what? G. Same goes for Earth also. For Earth, the mass of Earth, Mth, equals to Gh Rh squared over G. So to get this divided, so the mass of Moon to mass of Earth equals to, divide this by this. That's Gm Rm squared over Ge R squared. Why? This and this will cancel each other as in divide. So now let's put in the value. So the mass of Moon to the mass of Earth equals to G of Moon over G of Earth times R of Moon over R of Earth all squared. The square is common. So with this we can continue. What's Gm? They're not given. What's Ge? It's Gm. Times what is Rm? They're not given. What is Re? Re is 4Rm. 4Rm all squared. This becomes from here Gm here 1, Gm here cancel. So I have 1 over 8 times Rm here 1, Rm here cancel. So 1 squared 1, 4 squared 16. So the answer is 1 times 1 1. 80 times 16 will give us 1280, and that is the answer. Now let's consider this question from 2005 math 32. A force of 200 Newton, let's call it F1, 200 Newton, acts between two objects at a certain distance apart. Let's call the distance R1, which is R. The value of the force, we are looking for the value of the force F2. When distance is halved, so let's R2 be half of R1. Half of R1. So if R1 is R, R2 is half of R1. So this between force and distance, we call the formula F2 equals to F1 R1 over R2 all squared. So F1 is 200, R1 is R, R2 is half of R all squared. This cancels this. So for this half, these two will glue up, this one will come down. So this same thing as what? F2 equals to 200 into 2 over 1 all squared. 2 squared 4, 1 minus 2, 8. So F2 is what? 800 Newton. So that will be the difference. This closer the distance, the more the force. Next, an object is weighed at different locations on Earth. What will be the right observation about its mass and weight? Simple. We know that weight equals to mg. The mass of the body is what we call the quantity of matter in the body. So if I have a cup that is half filled with water and I close it, so that cup will weigh the same thing, or the water inside the cup will always be half filled if no water escapes. So the mass always constant. Weight is normally ought to be constant, but because of this G varies, so weight also varies. So you can say weight very proportional to G, where mass is constant. The more the gravity, the more the value of the acceleration due to gravity, the more the weight of the body. So mass is always constant while weight varies. The question is, why does this G varies? G ordinarily equals to Gm over r squared. This is what? Mass of Earth. So why this G is the value of acceleration? So mass of Earth is constant, yes, but the density of Earth is not, fixed. Some part of Earth is sand, solid. Some part, are made up of, liquids. So because the density is not constant, the mass also changes in a way. So this variation in density can affect the value of what G at a particular place. But if you are dealing with total mass, it doesn't affect it. But the most important thing is this value of R. R changes from place to place on Earth. If Earth is a perfect sphere, then distance from every surface will be constant. It will have a constant radius. But because Earth is a perfectly sphere, the shape is called geode. It is almost flat at the top and bottom and body at the sides. So let's say this is the center. As you can see, this point is closer to the center than this point. And the farther you are, the more the what? The farther you are, the lesser. Because if you are very far, R is big. If R is large, G is small. So gravity here will be lesser than the gravity here. So if you move from place to place, why the value of R is changing, as R is changing, G also changes. So one of the factors that affect the weight of the body not being a constant, or we can say the weight of the body varies because acceleration to gravity varies. That is one. Secondly, why does it vary? Because of the shape of Earth. The Earth is not perfectly perfectly spherical. That's another reason. So meaning at every position on Earth, at every point, the radius will be different. So you can also say difference in latitude and longitude can also be part. The last question here: a satellite moves in a circular orbit of radius 4r. So what is Earth? So we have a satellite here in a circular orbit. The radius of Earth alone is r. But this satellite is distance 4r from Earth. So then I ask, the acceleration of the satellite in terms of G is. Now this is about distance and acceleration. You recall I gave you that G2 equals to G1 into R1 over R2 all squared. So the G2 is the value of acceleration to gravity for the satellite. G1 is acceleration to gravity on Earth, that's G. While R1 is radius of Earth, that is R. While this R2 is distance between the satellite and Earth, which is given to be 4R. That be 4R all squared. From here, it means G2 equals to G into RA1, that's 1 over 4 all squared. 1 squared, 1. Then 4 squared, 16. So it means G2, which is what? The acceleration to gravity on that satellite. Then call it GS equals to GF over 16. So it will be 1 over 16 acceleration to gravity on Earth. So meaning if a body is very far from Earth, its value will drop. On Earth, G is 10. So 10 over 16, that will be gravity on that satellite. So if you have scientists on that satellite, what happens? They will almost be floating there because the force that will pull them to the satellite will be very less. That's why when you have a spaceship, or when you have rockets and they show the scientists there, they're always floating because the gravity there is very what? Very small. So the further you go from Earth, the lesser the gravity, and the less attached will be on the ground on that particular region. Then your tendency to float will increase. And I think with this we can end questions on gravitational fields.